Alright, so, yeah, so we're basically, if we have something with constant acceleration, right, we can then take the integral to get what function? Velocity function, yeah. So if we take the integral, if we take, well, you know what, yeah, let me, so if we take the integral, it'll give us, so if we, the velocity is the integral of the acceleration function dt. So our acceleration function is just what? The acceleration function is what? No, just what is our acceleration function? Hey, so it's just a constant, it's just a number, right? All right. So we're gonna so the velocity then is going to be the integral of this constant dt. What's the integral of a constant? 0. Oh wait. A multiplied by t. It's the constant multiplied by t. So a times t, however, plus c. Yes, we got to do plus c just in case. But then we can use these initial conditions to find out what c is. Because we know when time equals 0, what's the velocity equal to? V naught. So we'll say v naught equals a times 0 plus c. So that means c equals v naught, which gives us then the velocity as a function of time, or the final velocity at any moment, is equal to v naught plus a multiplied by time. And that's omega right there. So there's omega right there. So if you have any constant acceleration, as long as the acceleration is constant, that equation will work. Omega right there. So vt equals v naught at. Yes? We all right? So this is now our velocity as a function of time. What I'd like you to do now is, what would I need to do to get the position as a function of time? I would integrate the velocity function. So I'm going to integrate the velocity function to get the position function. So what I'd like you to do, integrate this and see if you can find beta. Given that the at time t equals 0, the initial position is x naught.
Find beta.
So go ahead and try that.
Find beta at lunch, guys. Find beta at lunch. Find beta at lunch, guys. We're near the front. Find beta at lunch. We're next to the pole.
Yes. It's gonna nobody wants to go to
Just give all the numbers to us, bro. You want to bring guitar today? We're gonna play a bunch of wait for beta. That's the wizard.
All right.
Let me get your area.
So let's do this thing. I'm doing the integral of this velocity function. So instead of vt, though, I'm going to replace it with what?
The ones where it's like,
So it's the integral of
where it's like the,
v naught plus at, right? So I'm going to do the integral of v naught plus the acceleration multiplied by the time dt. Yeah. Yeah.
You said to find the acceleration, just slope, right? On that graph.
Yeah.
See, delta y over delta x in that situation is a long because x is referring to position.
Yeah, I would not use that notation. I would not use that notation.
So it'd be delta v over delta.
Correct. Yeah. Yeah.
Oh my god.
So, okay, I'm doing this integral. V naught is what? It's just a constant. It's just a constant. So what's the integral of a constant? So this is going to be V naught t plus, yeah, this we got to add 1 to the power. So it's going to be at squared, but then I have to multiply it by 1/2 because I have to divide it by that power. All right, and then plus c. But then we got some initial conditions. When time t equals 0, the initial position is 0. So we can replace this with x naught equals v naught multiplied by 0 plus 1/2 a times 0 squared plus c. So that means x naught is our c. So that gives us then the equation that the position as a function of time is equal to the initial position plus the initial velocity multiplied by time plus 1/2 times the acceleration multiplied by time squared. And that's beta right there. Which, because if I subtracted both sides by x naught, I get the final velocity as a function of time minus the initial velocity, which is just the displacement, equals v naught t plus 1/2 a t squared. But in this class, we're going to generally use this notation. Yeah. Questions, comments, concerns about what we just did? Yeah. Oh. So, again, I saw some people, just did like almost like 4 lines, to get to these, So, I just want you to appreciate, because here's what we did in honors physics to get these equations.
The not fun way.
Yeah, the not fun one.
So we used a velocity time graph and had to find the area under the curve. We found both areas, but then we had to replace certain things. So we had to go to this acceleration graph, and then we replaced that all, and then we finally got there.
So bad.
Compared to what you guys just did is integrate once, boom, there you go. Integrate twice, boom, there you go.
I'm so glad it takes us a second here.
Okay.
Wait, xt minus x naught.
So yeah, questions here, comments, concerns.
No.
All right. So what we're gonna do now?
What's the
Xt minus x naught, that's basically minus initial.
Correct. Yeah. Xt is often just said x. It's just the final position at any moment. Yeah.
What's the integral of beta then? Because I understand.
It doesn't mean anything after that. Okay. There's no math. It's like finding the area under the graph of a position time graph. It means nothing. So not every integral or derivative has physical significance, but yeah. So while you can keep taking derivatives of positions to velocities to acceleration. Yeah. Yeah. Okay. So I just want to emphasize here really quickly, a plus is going to help us derive alpha right there. I want to emphasize that this is the initial velocity, this is the final velocity. Sometimes we use v naught and v. So that's okay. But these are different things. Initial velocity, final velocity, average velocity. So they're different things. So in these problems, you're always going to have some initial moment and some final moment.
Yeah.
So you want to be able to differentiate between those things. So for example, in this problem, here's a person moving at 1 meter per second, undergoing constant acceleration, and then going to 3 meters per second. So I want to emphasize the acceleration is constant here. So acceleration constant. So they're basically gradually going from 1 meter per second to 3 meters per second. The initial time is 0, so oftentimes you're going to see that. Often, like 90% of the time, the initial position is also going to be 0, but not always. So, and that's one of the reasons we're, yeah. Well, and then the final time is 6 seconds. The person's moving 3 meters per second. And the initial position of the person is 2 meters. The final position is 14 meters. So that's what we got there. And again, the initial velocity is not the final velocity, and it's not the average velocity. So they're 3 separate things. Sometimes they're all the same. Sometimes. But that's a very special case. That's like maybe 10% of the time. So they're different things. So what I'd like you to do, just kind of show how they're different, is I would like you see if you can calculate the average velocity 2 different ways.
Wait, what?
So there is the situation. Calculate the average velocity 2 different ways. 2 different ways. So see if you can figure that out.
Yes. That's what I did. Average. That's what I did.
So isn't it 17?
No, that's what I did. You know the homework.
Yeah.
How many seconds is the second velocity?
That's what I did. That's like
So it starts at t
more,
equals
right?
0.
I'm like
It
negative.
ends at t equals 6.
I don't remember what I got, but that's what I did. I'm looking at this, but
Wait, it's
I'll give you 1 more minute. Yep.
it's not changing velocity.
It starts at 1 meter per second and then becomes
Adding these two and
3 meters per second.
It's equals 6, right? And we're only going from 0 to 6, so therefore it doesn't go to 6.
Look at this.
Is it stopping at 6?
No, it's like this. It's like this. So you don't start yet. Now you start, but I'm moving down. Now you stop. Oh. Yeah. That's one way to do it. So, all right.
1 + 2.
What's one way you calculated that average velocity? Yeah. The final velocity?
The delta x over delta.
Change in what? Not velocity. Speed. Not speed. Position. Yeah. So we could use the change in position over the change in time gives you the average velocity, right? That's the slope of a position time graph is one way to calculate the average velocity. And we've got the positions. There's 14 minus 2. So that'll be 14 minus 2 divided by how much time took place? 6 seconds. So that, whoa, hey, what's up? Whoa. So that's going to be 12 divided by 6, which is 2 meters per second. Circle. And then, what is another way, though, you could calculate the average velocity?
Can you go back up? And give me the 2 Okay, thank you.
Yeah. Yeah. So this works only under constant acceleration, by the way. Can I scroll down now?
No, you're good.
Okay. This only works under constant acceleration. Is we could take the initial velocity, add it to the final velocity, and divide by 2. That's the definition of an average, right? So if you have 2 numbers, to take their averages, you add them together and divide by 2. If you got 3 numbers, you add those together, divide by 3, etc., etc. This only works under constant acceleration, by the way. So some of you tried to do this on your quiz to find the speed, but it didn't. But it was not constant acceleration. It was not constant acceleration. So we get that the average velocity then is 1 plus 3 divided by 2, which is also 2 meters per second. They mean the same thing. There are 2 ways to calculate the same thing.
So as long as they're straight piecewise functions, we can probably use the same.
I'm not sure what you're saying. Say it to me again.
So it's like that. You can probably still do the same method because of straight line.
I would break it up into 2 parts. Basically, we're going to deal with that in just a moment, actually. Okay, so now what you guys are going to do Well, you're going to use these two equations to get alpha. All right, you guys are going to derive alpha. You should all have markers on a whiteboard. You're going to work with a partner on this. So, and I'm going to get you started. Here's how I'm getting you started. If A equals B and B equals C, what can you say about A and C? They're equal to each other. Is that what that's called?
Yeah.
So, set those two things equal to each other, and then you can use beta or omega as well. See if you can get to alpha. See if you can go from here and get to alpha. That's your goal. Go ahead. Alright, so, yes, you're sitting at rest in a car and accelerated at 4 meters per second squared. How long until it reaches 50 meters per second? So, how I recommend solving problems like this, so we're going to, now, graphing is still useful, it can help, but we're going to kind of get away from graphing and start solving problems with variables and equations, stuff like that. And steps you want to take to solve these problems is to draw a diagram. Draw a diagram of some sort. You label that diagram. So I know for students in the past we had BOVAT. Well, because I'm sticking to the APC equation sheet, their format, this is now a BOVAT. I know. It's all right. So the initial velocity, the final velocity, the acceleration, the initial position, the final position, and the time. So yeah, in the past we combined these two with the assumption that the initial velocity, the initial position is 0, and we can still assume that most of the time. So most of the time that initial position is going to go away, but because I've seen problems on the APC exam that involve simultaneity, this is going to be easier for you with those problems. Then you choose an equation. You choose an equation, alpha, beta, and omega, to solve. Sometimes you need more than one equation. So then you solve, and then you always check yourself. So ways you can check yourself is, if it's moving at 3 times 10 to the 14th meters per second, that's impossible. That's faster than the speed of light. There's no way that can happen. So if you know for a fact the object should be moving to the right, but you get a negative answer, maybe something's wrong there. Or maybe your initial assumption was incorrect. Or if the units don't work out, maybe something's wrong there. Okay, so what I'd like you to do, go ahead and do this and try and solve for, how long does it until it reaches 50 meters per second. So you start off at rest, 4 meters per second squared. Oh yes, and your picture does not need to be pretty. So
How do you check?
you can see, what's that?
Like, check, you just go over it again, like, I don't know.
Well, like I say, you can check units.
Oh,
Check,
okay.
does that number seem reasonable?
Okay.
Positive and negative direction things. Thank you very much.
Hey, show me your map now. Show me your map.
So we had initially. What were you using? Alpha. Is it?
Wait, omega.
Oh, you did it.
Oh, and it says how long, not how
So I'm only going to give you guys about 30 more seconds because I want to pick up the pace here because I want to give you back to quizzes and stuff.
It's like every time there's no turn, like I said, and then every fucking 6 all that shit.
Because these are like silly walking dogs.
Asking for the
All right. So, here we are. Here's my diagram. You can even forego drawing that card, just draw a dot. It's fine. It doesn't have to be pretty. It doesn't have to be like, you know, what Nadia can do over there by drawing Carlos the Lemur over there.
Carlos, Carlos sexy little lemur. Wait, it's Julian. Wait, just Julian. It's Julian.
Yeah, it's Julian. Okay. All right. So, one thing you want to do as well is establish an origin. You get to choose the origin. It's up to you. And a good place to choose the origin is wherever your initial moment is. Wherever your object is at its initial moment. So there is my origin, right there. And you always want to choose some initial moment and some final moment. So my initial moment is going to be when the car is here at this velocity, and my final moment will be when the car is here at 50 meters per second velocity. So you get to choose those things, and you just want to choose whatever's most convenient for you. And so my initial position is here, my final position is here. What do I know? My initial velocity is what? 0. So that's something you're going to have to do is if it's at rest, oh, that must mean that the initial velocity is 0, right? If it says starts at rest. What else do I know? Final velocity is 50 meters per second. What else do I know? Acceleration is 4 meters per second squared. And then I'm going to say, I also know my initial position because I put my origin there, it's 0. What could I use to solve for this? Alpha, beta, or omega? Omega be the way to go, so V equals V naught plus AT. Typically in physics, we solve in variable form, then plug in. So I'm going to solve in variable form, V minus V naught. I'm going to subtract both sides by V naught, and divide by A to get the time. So I can plug in now, that's 50 minus 0 divided by 4. So the time is 12.5 seconds. Hey! There it is. Questions, comments, concerns so far? Yeah. That's the final position, which I don't know. Yeah, they didn't give me it. Is that, yeah? All right. So next up, you're traveling at a constant 50 meters per second. When suddenly you see Carlos. When you see Carlos jump in front of the road 125 meters ahead of you. What acceleration do you need in order to not hit Carlos? What is the acceleration? We're going to assume that you slam on the brakes at this moment. So go ahead, see if you can figure that out. I'm going to give you guys just like a couple minutes. I'm sorry, but I want to go through this.
Damn. Do it. I give consent.
All of this is on video, by the way, so you know it's a legal document. If so, try
Consented.
you know this problem.
What?
Don't interview.
I do know this problem.
Bye. All right. So once again, you might be doing this. I'm sorry. I'm just gonna keep going here. Go back. So some things I know. Let's see. I got my initial velocity here. My final velocity, if I want to not hit Carlos, where do I have to be when I'm at Carlos? How fast am I going? Sorry, how fast am I going when I reach Carlos?
0.
I should be going 0. So my final velocity should be 0. So, and typically we just draw a dot. That's vector notation for 0 or something. No arrow. So other things I got, I'm going to still establish my origin right here. So this will be my origin. That's also going to be my initial velocity, my initial position. So, and my final position will be what if I want to not hit Carlos? Yeah, 125. So we're saying that it's going to be like centimeters before, but like it's basically just going to be 125, right? Okay. So, what else? Oh, what would be the direction of my acceleration if I'm moving to the right?
Negative.
And I'm slowing down. Yeah, it's going to be negative. And we can check that with the math in just a moment. So, what do I know here? My initial velocity is what? It's not 0. It's 50 meters per second, because I'm cruising at 50 meters per second. At the end, it's going to be 0. We don't know my acceleration. That's what we're trying to find. My initial position is 0. My final position is 125 meters. And then, so I got all that. What could I use to solve? Alpha, beta, omega? Alpha seems like the best one to use. So I'll go v squared equals v naught squared plus 2a, and then the final position minus the initial position. All right. So now I got to solve for acceleration, right? I'm going to subtract both sides by v naught. And then divide by 2 and this quantity right here. So it's going to be v squared minus v naught squared divided by 2, final position minus the initial position, equals the acceleration. So I got 0 squared minus 50 squared over 2 times 125 minus 0. So, and what does that get you? Anybody who was able to get this? And good, negative, which confirms what we thought, that the acceleration was going to the left. So it's negative 10 meters per second squared. So, usually I would let you go into do this, try to do this on your own, but again, because of time, I'm going to blow through this. So, but questions here though, before I move on, of what we just did. So again, we're setting up a diagram. All right. So we're going to use. So I will say, if you set up your origin, well. Here's the thing. Reaction time is 1 second. So how fast are you going when you hit 4? Hard.
Let's go. I only give you permission, Trivine, only you.
So here's the deal, though. You're 100 now. If you slam on the brakes, you are at the mercy of friction, because the way brakes work is all they do is they lock the wheels. So now there's rubber and concrete rubbing against one another, and you are at the mercy of friction to stop you. So thank goodness for friction, or we wouldn't get anywhere. So yeah, to stop you. So that's the thing, though. You're 125 meters ahead, and you have no choice once you slam those brakes but to accelerate at negative 10 meters per second squared. You have no choice. So that is the acceleration, no matter what, whenever you slam brakes. But reaction time is 1 second. So you're 125 meters ahead. You see Carlos, but your brain goes, so the light comes in from Carlos. Maybe it's at night or something, so the moonlight hits Carlos, right? And then it bounces off Carlos, reaches your eye. Your brain recognizes that and goes, "Oh my God, that's Carlos!" Oh no! And then another electrical pulse is sent to your foot. Then, like, "Oh, I don't want to kill Carlos." So my foot needs to, right? But as this is happening, what's happening to your car? It's moving forward, right? And then finally it reaches your leg and you go, "Whoa, no," and then you slam on the brakes. So at first you're traveling at a constant what? 50 meters per second. So you don't start to accelerate though until you slam on that brake. So how far have you traveled? You've traveled 50 meters. Now, it's a pretty, not such a bad calculation, right? But let me at least kind of emphasize here. So we're saying between here and here, right? What's your acceleration?
50.
Your acceleration is 0, right? So, but then from here to here, what's your acceleration?
-10.
So yeah, here your acceleration is 0. Here your acceleration is -10 meters per second squared. And these equations, what have I said? They only work when? Constant acceleration. There needs to be constant acceleration. From here to here is the acceleration constant. No, it is not. So what you do just like what we did with the graphs and the sharp points. You split it. You go, nope, this part, then this part. Two situations are going to happen here if there's no constant acceleration. Either the AP exam is going to give you an equation that models the acceleration, and therefore you got to use calculus to solve it, or if it's an abrupt change in acceleration like this, you can split it into two parts. So we can solve for, that's what we're going to do. So here's going to be part A. Here's going to be part A. And then over here I'm going to do part B. So for part A, now if I have 0 acceleration, the only things that are going to matter, it doesn't, if you want to say divot you can, but is the, yeah, this is a little exhibit? I don't know. Is the initial position and final position, well, again, I'm making this 0, so my initial position is 0. My final position would be what I'm looking for, what this new position is. I'll call it position 1. That's the new position right here. Position 1. Oh God, I'm running out of time. Let's see. The speed is 50 meters per second, right? And the acceleration is 0, and the time is 1 second. So we can basically use the fact that, and I'll write it there, this equation here, which is basically delta x equals the average velocity multiplied by the time. So, which this is the final position, x1, minus the initial position, which is 0. So this is 50 meters per second multiplied by 1 second. So my final position here is going to be 50 meters. So that's part 1. Now I know how far I've gone from my origin once I slam on the brakes. And that new position, that new position there is going to be, I'm going to call this x1, x2. So that new position is now this position. This is 50 meters. The final position, okay. What's the final position?
75.
That's the displacement. What's the final position? If this is the origin, what's the final position? So the final position is 125 meters. Oh, crap. Your acceleration is -10 meters per second squared. We're looking for the final velocity, and we know our initial velocity is what? 50 meters per second. And so, which equation could you use, alpha, beta, or omega, to solve for this? Alpha. Alpha. And then you should be able to solve from there. So I'm going to give you guys your quizzes back. Oh, before I give your quizzes back, first thing, when I give you your quiz back, before you leave, put it back right here. So nobody should leave with their quizzes. Second thing, tomorrow we're going to be dropping stuff. So bring in an object. It should be big. Not big, like this, like this would be great, you know. So you're gonna drop, but we're gonna be dropping stuff, and so you're gonna bring in just any object you want. The only thing you don't want, don't make it so it has high air resistance. Okay, that's bad. You want it, you know. So bring it. Zach Kim.
I'm not leaving.
Brittany. Mark.